Consider this simple system of equations. We are looking for a point x, y that satisfies all three conditions. But geometrically, it's impossible. A perfect solution does not exist. This is the reality of real-world data. It's noisy and contradictory. So, what do we do when our system Ax equals b is unsolvable? We don't give up. We find the best possible compromise. And the way we define best is by finding the solution that makes the sum of the squared errors as small as possible. This is the story of the least squares approximation. Welcome to Decoding Complexities. I'm Pradeep. To understand this, we must reframe the problem in the language of vector spaces. The equation Ax equals b is asking, can we find a combination of the columns of A that perfectly equals the vector b? Geometrically, this means, does our target vector b live inside the column space of A? As we can see, the answer is no. This is why the system has no solution. Any vector Ax we can possibly build must live on this plane. We can't reach b. So, we need to find the vector on the plane that is closest to b. Let's call this closest possible vector as p. The error in our approximation is the leftover vector e. Our goal is to find the solution x hat that makes this error vector e as short as possible. And minimizing the length of the error vector e is the exact same thing as minimizing its squared length. The squared length is just the sum of the squares of its components. This is the sum of squares we are trying to minimize. This is why it's called the least squares method. So, how do we find this shortest possible error vector? The clue is in the geometry. The error vector e will be shortest when it is orthogonal to the plane C of A. This means e must be orthogonal to every vector in that plane, including the columns of A that defines it. We can express these conditions compactly using the transpose. The statement A transpose multiplied the error vector E equals 0 is the mathematical way of saying the error vector E is orthogonal to all the columns of A. Now we have everything we need. We just substitute our definitions and derive the solution. First, we know the error vector E is the difference between our target vector B and our projection vector P. And we know our projection P is the best possible answer we can build. So it must be A multiplied with x hat for some optimal x hat. Now, we just distribute A transpose across the terms. And finally, we rearrange the equation to get our master result. A transpose A multiplied with x hat equals A transpose B. And this is the elegant heart of the solution. These are the normal equations. We started with an unsolvable system, used the geometric condition of orthogonality to minimize our squared error, and transformed it into a new solvable system for the best approximation x hat. This new equation, A transpose A multiplied with x hat equals A transpose B, gives us a direct way to calculate the best fit solution. Let's solve our original problem in Python. First, we define our matrix A and our vector B from the unsolvable system we started with. The left-hand side of our equation is A transpose multiplied by A, and the right-hand side is A transpose multiplied by our target vector B. We now have a simple solvable system. Left-hand side multiplied with x hat equals right-hand side. We ask NumPy's linear algebra solve method to find x hat for us. It's more stable than calculating the inverse directly. And then we print the result. We get 1.667, 2.667. This is the single point that represents the best possible compromise, the one that minimizes the sum of the squared errors for our original contradictory equations. This isn't just a trick for abstract systems. This is the engine that drives linear regression. When you have a cloud of data points and you want to find the line of best fit, what you are actually doing is solving the normal equations to find the parameters that minimize the sum of the squared errors. We started with a contradiction. We defined best as minimizing the squared error, which gave us the name least squares. We then used the geometric clue of orthogonality to derive the normal equations, a new solvable system for the best fit answer. If this deep dive was valuable, hit that like button and subscribe, because now that we have this tool, we are ready to cross the bridge and begin our series on the math of linear regression. Thank you for watching, and I will see you in the next one.